Okay.
And yeah, I think it's recording now.
Okay. Great. All right. Apologies for the interruption, Eric. Please continue.
Yeah, no worries. Yeah. And also, I don't know what the standard is here, but feel free to interrupt me with either vocally or I've got the thing with hands on the screen. So
okay, cool. Yeah. People will tend to interrupt if they want to. So yeah.
Sounds good. And so if you ask what the star formation rate is in the early universe, you can measure it out to a certain redshift, and then you can measure it in the optical out to a higher redshift. And there's a gap of a factor of about 10 between the two. And so the question is, what is the actual star formation rate that we don't see in the optical because dust is in between us and the stuff that is forming stars? As you'll notice in the plot on the left, there's a big range out to the right in the infrared. Infrared in this case meaning also millimeter wave, that we don't really have any information about. So the question is, how can we probe that? I promise this will get back to fundamental physics soon enough.
Just so I understand the previous slide, Eric, the left one is star formation rate in solar masses per year or something. Right. On the previous slide, and the right slide is dust opacity or something.
Solar masses per year per megaparsec, I think.
Per cubic megaparsec, yeah. So what's the one on the right? What's the y-axis on that one? That's is that dust opacity or something, or?
Yes, I think you're right. Okay. It's a bad slide to include, but
okay. We should be focusing on the left, is what you're getting at. Okay.
I don't actually quite know what it means, but I think you are.
Okay, it's got the D, so it has to be.
Yeah. All right. So if you look at the spectrum from these individual galaxies, you find both a continuous spectrum, which is shown here, which is mostly a black body. It's a black body with also some ultraviolet radiation. But it also has a number of spectral lines. And if you remove the baseline from that, you can look at the lines individually. And there are a number of them that are interesting. So there's, in particular, it's not actually on this, not actually in the legend of this, but carbon plus, or C2, as astronomers call it, is one of those lines that we care a lot about. And that's particularly interesting as a tracer of star formation. So it's a molecule that gets excited by radiation very near to hot, in hot environments. So it's a tracer of how much star formation is going on. There's also carbon monoxide, CO, which is nice for a couple of reasons. So it's a medium temperature gas that's in the kind of away from stars and galaxies. And that tells us a lot about the structure of the galaxy itself, and is going to be interesting. All right. And so you can ask, where do these lines fall in the atmospheric windows that we're able to observe from Earth? And so the atmospheric windows are basically determined by the gases and water in the atmosphere. And so the ones I'm going to talk about particularly, there's one from about roughly 1 to 1.5 millimeters, which is kind of the classical 150 gigahertz CMB band. And then there's one that's at a higher frequency, and then there are more that are at even higher frequencies, which I won't talk too much about in this presentation. All right, so you can do this in a couple of different ways. You can either look at individual galaxies and measure their spectrum, or you can make a map of the sky, and then you can ask, where are the galaxies in both X, Y, and Z? And you can ask, where are the galaxies in 3 dimensions? And if you have a spectral line, the fact that all the galaxies are moving away from each other based on cosmological expansion, tells you that if you know the frequency of a line, you know where it is compared to you. So you can map frequency to distance. And so you can make a three-dimensional block that maps the position of each galaxy. And in this case, by galaxy, I mean an unresolved object that is bright. So we're not looking at the details of the galaxy itself. We're looking at the fact that the galaxy is emitting something. And if you do this spectroscopically, you can actually measure where each galaxy is as a function of its distance from you. So you now have X, Y, and Z. And so that's really interesting, right? That tells you a lot about the structure of the universe itself. So here's a quick cartoon of the history of the universe, where you go from the Big Bang off at the very left, and then the CMB, when everything was a plasma, then everything recombines. And then you have the first stars start to turn on. And the distribution between the distance between the stars to turn on tells you a lot about how that happens. And I'm saying the word stars, but actually it's not totally clear how much of that is due to quasars or other things. So there's some interesting astrophysics associated with what the objects associated with this epoch when the first objects started to emit ultraviolet radiation turned on, which is sometimes called the end of the Dark Ages, or reionization is the sorry, I'm completely blanking on the word, but it's the point at which the first ultraviolet photons started to make the hydrogen atoms in the universe neutral, so they no longer absorb radiation. So photons can free stream. So you can do this in a couple of ways. You can look at individual sources, which is one of the things that very many instruments, including one I'll talk about, are involved in. You can also try to make a map of all the sources you can see. So on the far left is a 250 micron. So this is below optical, but visible in the wavelength that behaves like photons range, and you get the very brightest sources, and that's basically what an optical telescope gives us. The other option is to make a map of everything, including the small sources you can't actually see, which is represented by what's on the right. This is at higher frequencies than what I'm actually talking about, but is representative. All right, so what do you get when you do this? So you make a map of the sky, and you have X and Y.
So Eric, I want to interrupt and just ask a question about those previous two maps. So if I understand right, those are the same sky, and the one on the left is, I have an instrument that has a sensitivity of 20 millijanskis, and I find all the circles in there that are sensitive to that, right? And the one on the right is, I actually made a map of all the intensity of everything, but with the same angular resolution as the one on the left. But I'm doing total intensity mapping, not just picking out the bright spots, but I've got something that keeps all the rest of the wavelength fluctuations or whatever, right? And okay, but they're both zero noise maps, right?
Yeah. So there's no noise in either map.
Okay.
I believe they're both Kepler images with the same instrument.
And what's 1200 per square degree? Oh, 1200 objects per square degree, or 1200, because there's no objects on the right.
Well, there are. They're just...
Okay. You're saying if I count those dots as objects.
Yeah, I think that's true.
Okay.
There's an underlying distribution of objects. Yeah, that's leading to those things. Yeah. So I think what that's saying is that the one on the right is due to objects of smaller and smaller mass or size or something, intensity. It's not a continuous distribution of gas contributing to that. It is.
Right. That's what I was asking. Are those objects on the right, or is it intergalactic?
So this is a noise-free map, essentially. I think every point source is actually a star, or in this case, a galaxy.
Okay. Okay.
Yeah. So there are a number of ways you could analyze this. One is to figure out what the power spectrum of the objects is. So a number of people have worked on this. This is work from a postdoc working with me, Erik Shirokoff. And the basic idea is that if you just sum up how much power there is as a function of spatial frequency, so small things are on the right, big things are on the left, you can actually distinguish between the different sources of power. And so there's what's called a clustering term, which is essentially the fact that galaxies tend to live near each other. So if you just make a map of the sky, big objects tend to be clustered together. It's not surprising, it comes out of modern cosmology. And then on the far right, you get what's called shot noise or Poisson noise, which is basically just the fact that there's some randomness in the distribution of objects. So if you put two galaxies totally at random, they have some, if you put a number of galaxies totally at random, there's some power spectrum associated with their distribution. All right, so what can you do with this? There are a number of things, and I'll talk about a few of them in a moment. One thing that is really cool is if you, sorry, I'm repeating myself, but if you assume that the C2 or C+, this is double ionized carbon emission, traces star formation. The fact that stars form also makes the neutral hydrogen in the universe transparent. It ionizes the hydrogen. And so at very large scales, the densest parts of the universe the densest parts of the universe do ionize hydrogen. And at very small scales, the places where galaxies form are associated with the densest parts of the universe. And so you get this really nice crossing of zero so on the right is, on the y-axis is the signal you get from ionized carbon, and on the x-axis is the distance scale in megaparsecs. And so where you're at very large scales, galaxies don't form where there is neutral hydrogen, or I guess actually the way to say it is neutral hydrogen doesn't exist where galaxies form. On the right, galaxies form in the dense parts of the universe where there is neutral hydrogen, because there's lots of everything. And so you go from a negative correlation where the stars aren't where the hydrogen is to a positive correlation where the stars are where everything is, including the hydrogen. And so you get this really nice crossing of zero, which is a really impressive diagnostic of both this technique and our model of the early universe. All right, so sorry, looking at chat. Other things you can do with this. One is to look for very early galaxies in a way that captures many of the galaxies that aren't captured by optical telescopes. So in particular, so this particular slide is written for time, which is a millimeter wavelength spectroscopic instrument that's going to be deployed in Colorado, in Arizona a couple of couple of months from now. And so you can ask, well, what can we say about cosmology in general and fundamental physics based on the history of based on the observation of these early galaxies. And so one thing you can do is you can look at very early galaxies in a way that you can't do with optical telescopes and try to map out the history of the expansion of the universe. So this is, the Hubble expansion, which famously has recently had a number of controversies regarding whether there are differences between the local and remote value of that expansion. And the idea here, so this is time, but basically this is any millimeter wavelength instrument, could allow you to explore some of that history in a way that you really can get to with optical telescopes, which is something I'm excited about. All right, the other thing you can do with this is basically add it to your cosmological data set. One of the suppositions that experimentalists like me have always included in our discussion of cosmology is the assumption that the statistics of the fluctuations in the early universe, the hot and cold distribution, is Gaussian. And you could ask the question, is it actually totally random? As far as I know, nobody has really answered that question yet. And one thing you can do with spectroscopy is you don't just map out the X and Y power, but you map out X, Y, and Z. And so in principle, you can figure out whether the correlations in Z have changed as a function of time. And that allows you to ask the question, is it actually totally random as the versions of inflation that people like me learned and have taught in classes would suggest? Or is it actually more complicated? Is there something that makes points that are separated in distance know about each other? And one way to figure that out is to separate planes in the Z direction, how far away it is from you, in addition to X and Y. Then the final science target that involves fundamental physics is the question of whether you can do what's called de-lensing. So the CMB is it's many things, but it's among other things a distribution of high and low peaks in physical scale, and you can measure that, but it gets modified by all the stuff that the photons have to pass through on their way to you. And the scale of the stuff they have to pass through is really important. And so one question is, can you do a better job of removing the interference from the stuff those photons have to travel through, in particular gravitational lensing, due to, galaxies and clusters in between the CMB and us. And one question is, can you do better at that if you have a camera that has multiple frequency channels instead of just a couple of channels? And I think the answer we've come up with is you can do a little bit better. It doesn't help you a huge amount. So the plot on the right is signal to noise versus, I think, versus a camera model. And the basic answer is you get something like a 10 to 15% increase, which is not bad. I mean, many of us have spent our lives trying to make a 10 to 15% increase in signal to noise ratio. So it's not terrible, but it's not a home run. It doesn't entirely solve that problem. All right, so how do you actually do this? So now I'm going to jump into some device physics and such. Trying to look at the time. I'm running very slow, so I'll skip a couple mini slides. So the traditional way to do this is using a gradient spectrometer, same as the optical spectroscopy and prisms that we've all used in class. But in order to do this at millimeter wave wavelengths, the size of the object has to be meters in scale. So it has to be a really large object. So this is Z-Spec, which is an amazing, really cool scientific instrument. But it has a single pixel and is the size of the table in your kitchen. It's enormous. And so the goal is to see if there's a way to make this smaller. So I'm going to talk mostly about a project called Superspec, run by a bunch of different people, led by me, also folks at Caltech, a number of other collaborators. And the basic idea is that instead of using a gradient spectrometer, you want to send radiation in along port 1, shown here, down a transmission line, and then couple it to a resonant filter, and then couple that resonant filter to a detector, which is written as an R, as a resistor in this particular representation. And each individual channel can be very narrow. You can change the resonant frequency by changing the length of the resonant transmission line. You can change the width of that channel by changing the coupling capacitor. And so in principle, you can vary everything about that detector, including its width and its frequency. And if you put several hundred of them together, you get almost total absorption, and you can sort your millimeter wave frequencies into channels. So the hard part about doing this is that you need a detector that you can deploy in the tens of thousands easily. So what we use is called a kinetic inductance detector, which is either a KID or an MKID, depending on who you talk to. And so when a piece of metal goes superconducting, the DC current travels with no obstructions, and basically you have zero resistance. But the electrons that make up the DC current, Cooper pairs in this case, still experience momentum. And so if you put an AC current on them, they have to slow down and reverse direction fairly often. And so what that does is it causes a phase shift between the voltage and the current of the Cooper pairs, electrons that are paired together, in a way that is mathematically identical to a inductor and inductor. And so what that does is it gives you a phase shift between current and voltage that you can call kinetic inductance. And that is something you can measure by measuring that particular phase shift. The other thing to know about superconductors is that if you shine a photon on them, a photon with enough energy that breaks them into pairs, the number of pairs changes, and that means the inductance changes. And if anything changes, when you shine light on it, someone can make a detector out of it. And so that's what we do. And so basically you've got this inductor, which is made out of just a wire made of superconductor. You couple it to a capacitor. You weakly couple it to a transmission line. Eric,
can I send you back a slide?
Sure.
You said something there that you know, I guess I hadn't realized. It says to first order LK is constant, but to second order it varies linearly with number of pairs. I hadn't realized that was at second order. So is there any way to like sort of, is that obvious that the first order it's constant, the inductance? Or is that like you got to do some math to have that pop out?
Yeah, I think it's not. I don't have an easy way to write that down. I think.
Okay. So yeah. Okay.
Yeah. So if you go to zero temperature and no light shining on the thing, you get a constant.
Yeah.
And the perturbation breaking pairs is a second order term, I think.
If it's not easy, that's fine. I'll have to go learn more about it. But so I was just wondering if there was an easy picture.
Yeah, it's been a while. The Review of Modern Physics Zemoidsonus paper has some, probably actually defines that entirely, but it's a while.
Great, thanks.
All right, so you make an inductor, couple it to a capacitor, that gives you a resonant frequency. The cool thing about this is that every individual detector picks out its own resonant frequency, and so you can multiplex them very easily by just connecting a wire across a bunch of them. And then, so you shine photons onto the inductor, you go from the black curve to the red curve, you can read that out. And you can stack a bunch of them all in parallel or in series, and you get a bunch of resonances. So the way we make these is all using superconducting thin films on silicon detectors like this. And we make use of high frequency superconducting circuits in order to make this work. So there's a coplanar waveguide shown at the top and microstrip shown at the bottom, and that allows us to transmit millimeter wave radiation through a silicon wafer in a way that preserves most of the power. The other nice thing about that is you can make lots of cool devices. This is feed horns, antennas, a lens, in this case made of silicon. So silicon has a very high index of refraction. So it's like a magnifying glass, but higher index than glass. And then you can build little tiny antennas based on that, and also things that couple to the horns that are shown above. You can make a couple of different kinds. You can make them either by making a long transmission line that is resonant. So you can think of this as a piece of coax that has a specific length. In this case, it's half a centimeter long and made in niobium, but same idea. The other thing you can do is make what's called a lumped element kit, shown here. So you've got
So I'm sorry, Eric, on the previous slide, is that the details of the meander there? That's the L, is that right? Is that?
It's a little more complex.
Where are the photons here? I guess that's the.
Yeah. So this is the antenna.
Okay.
Up top. And then there's a very small region that's designed to be the inductive element, and it's meant to be. It's all defined with electron beam microscopy. So it's meant to be the smallest and most inductive part of this transmission line.
Okay.
And then the rest of it is easier to define lithographically. It's the kind of the capacitive part.
Okay.
But the whole thing is basically a single transmission line.
But the geometry of that transmission line is the thing that defines your L and your C, and therefore your resonant frequency.
Yeah.
And the photons are getting absorbed at the upper left there, and the feed is on the sort of connection to your electronics is on the bottom right.
So the L in the top left is higher, and the C in the bottom right is higher.
Yeah. Okay.
But they're matched impedance wise.
Okay.
So you can make a lumped element version of this. These are some devices we made for the Muscat instrument, that weird meanders, so it absorbs both polarizations, where you've got a inductor and then a capacitor, in this case, interdigitated using fingers that don't quite touch, that's weakly coupled to what's connected to it. I realize I'm running very late on time, so I'll skip through a couple of things. All right, so you build these things. You can ask how sensitive are they? And we now, after decades of work, know a lot about how the noise in these detectors works. So there's the fundamental noise, which is the noise associated with photons that hit the detector themselves. And that's kind of the target you're aiming for. There's something called recombination noise. So this is where Cooper pairs break apart and then come back together. Every time they do, you lose one conductor from your kinetic inductance circuit. Amplifier noise, which is easy to understand. There's a number of other terms. And then there's something called two-level system noise, which there's a little bit of a thing about it. So two-level system noise, the idea here is that on the surfaces of insulators, you can get individual molecules that have states that can flip back and forth between two different levels. And if they happen to flip back and forth between two different levels at the same frequency as your microwave signal, they'll do so more or less randomly. And they'll either absorb a photon or give up a photon at microwave frequencies. And so that generates a randomness to the signal you read out. And we don't have a very good microphysical model for it. Some people have worked on that, but there's a group at Delft that has done a bunch of work on that. But the basic idea is that even though we don't have an a priori reason to set an expectation for how much noise it generates, we know how it scales. So it scales with frequency, it scales with power. Lower power gives you less noise, which is surprising. It scales with temperature. Lower temperature gives you less noise, which is also surprising. And the model for that is basically that once you have enough thermal excitation, you end up populating the higher state, and these systems don't fall back into their lower state. So if you go to a high enough temperature, this noise goes away. It also varies with electric field, and it's a complicated function that's E cubed over E squared. So you have to do a lot of geometry to figure out what you would expect. But the basic conclusion is that basic conclusion is that, first of all, it's hard to predict from first principles. So you need to make one and then test it. And then the goal is to make surfaces clean, measure it, and then lower the electric field, increase the amount of power to the extent you can. All right, so how do you actually do this? So here's what one of our previous chips looked like. So the thing on the left, there's a big lens and then a tiny little antenna, and then the power comes down that line and goes off to a number of detectors with very big capacitors. And if you zoom in on one of these particular objects, it looks like this. There's a tiny little detector inductor at the top, very large capacitor, and then a coupling capacitor to the feed line. And if you zoom in at the very top, that's what the inductor looks like. So millimeter wave power goes down this feed line, couples to this staple shaped thing, which resonates, and then couples to the inductor itself that goes on to the capacitor. We built them. Here's what they look like in person. I'll skip a couple of slides in the interest of time. So here's a plot showing the amount of power received at the very end of that millimeter wave feed line versus frequency. So the black line is how much power it gets through. The colored plots are the power absorbed by individual detectors. So basically, we're just showing we've got a spectrometer here. The black lines with no matching colored lines are dark channels that don't have a matching detector. But we absorb 95% of the power and have a pretty reasonable grid of channels that detect power. And you can go into much more detail and zoom in on some of those individual channels. So this is work that Jason, sorry, I'm completely blanking on the name. This is work that a student working in our group has done, trying to fit the individual spectrum of the channels to an analytic model. And there's some discontent, some lack of resolution at the far right, high frequency, which we don't quite understand. But in general, we do a pretty good job, including all of the little bumps that are due to other channels. Measure the noise. It looks pretty good. For a R of 100, so this is total frequency divided by the fractional frequency of a channel of 100. This is where we'd expect the noise level to be. And our instrument is better than that for any temperature we're likely to look at. So the next step is to make the full version of this. So we've got a 300 channel version, which is shown here. There's a new antenna, and all of the rainbow pattern are the capacitors for the individual detectors. And so this gives us, in principle, a 300 channel resolving power of 300 readout at 200 to 300 gigahertz. So question is, what do you do with this? First step is to deploy it as a test instrument. And so we're planning to do that in the next couple of months at the Large Millimeter Telescope in Mexico. And the goal here is to basically make an instrument that looks at individual galaxies and resolves spectra. Telescope exists. We haven't taken photographs of the actual hardware, but it's all sitting in our lab, ready to go. And the goal here is to make a 6-pixel version of this that will just look at individual galaxies and allow us to measure the spectrum. And one of the things Chicago has been in charge of is working out the readout. And it turns out you can actually do pretty good with commercial electronics. So there's a Caspar-Roach system, which is pioneered by much lower frequency radio astronomers. It's a field programmable gate array with some hardware that allows you to reprogram it. And we've put together a system that allows you to put, well, in our case, 6, but in principle, any number of them together. There's also a lot of work being done both at Fermilab and McGill to make a better version of this, because the hardware is actually quite old. So where does this live in the world of astronomy? I think I might skip some of this, but basically the plot on the far right shows signal noise ratio given, I think, 1 hour of observation. And so we're really probing the very high redshift universe, Z of 4.5 to 8, with pretty good sensitivity compared to some of the other instruments. The blue plot on the left is our sensitivity to carbon monoxide lines and much lower redshift, which doesn't look terribly impressive, but has the benefit that it probes some of the CO transitions that aren't probed by other instruments. We're going to look at galaxies. And our final goal is to try to make a multi-pixel, what's called an integral field unit, which is basically just a spectrometer with multiple pixels you can point in different directions. All right, I'm very late on time. The other thing you can do with this is use it to look at the CMB, which is a very large part of what's called the South Pole Telescope Stage 4 or SPT-4 instrument. So this is a plot of responsivity versus the temperature, the black body temperature of the thing you're looking at. And what I find amazing about this is the linearity of it. There's a little bit of curvature, but basically this device is linear over factors of 100 in power, which suggests you can make a CMB detector out of it. And so one way to do that is you take an antenna, you bring the millimeter wave energy in from the antenna, and then you couple it to an inductor. So I think this is the baseline plan for the SPT-4 instrument, essentially. And we have some devices that have tested this. And so we've got some test devices. You've got an antenna, couples to the inductor, couples to a capacitor. You can read that out. Here's what it looks like in practice. This is all work that Amy Tang in my lab did recently, or a couple of years ago. Skip that. The other question is, how well can you actually measure noise, or is your detector sensitive enough to make the measurement you want? So this is a very weird unit that's used in the MKID world, fractional frequency noise, which is measured in 1/root hertz. So it's the square of hertz over hertz squared, which is kind of strange. But the colored lines, the red and blue, are the power spectrum that we measure for devices in the lab. And then the bright green at the top is what you would expect based on photon noise. So the statistics of individual photons hitting the detector for a very, very good site in the CMB. So despite the fact that we have this really ugly looking 1/f noise, we're still pretty good compared to what one would need. Yeah.
Is that a, before you were talking spectrometers, so you're talking about very narrow bandwidth detectors, right? This presumably is like a 25% bandwidth detector at 150 gigahertz or something.
Yeah, this is, I don't remember if it's 150 or 220, but it's a wide band.
Okay, and this is so you're no longer doing any of the spectroscopic sorting. Right. You're literally just taking all the power you can get and defining the band with other filters or something. Is that right?
Yeah, this is CMBS4 or
SPT4. Okay, yeah. Okay.
Yeah, not CMBS4. Sorry.
Yeah, there's a lot of 4s lying around.
Yeah, so I'm totally out of time, which I'm embarrassed about. We measure optical response. We've made versions that couple to horns, which I think is the path forward for CMB devices. So then the other thing that I'll mention in the last couple of minutes is the next step when it comes to spectroscopy. So one thing we've been working on is trying to increase the resolving power, so the resolution of the individual spectroscopic channels, and then figure out how to make a scalable, wide, scalable version of this that can be deployed with hundreds of pixels. So we have test designs, same design as the CMB kids. And I'll skip all of this. Sorry, I'm very bad at figuring out how long talks should last virtually. We have lots of test devices that seem to be looking good. And I guess the other thing that might be of interest to folks here is a new program which is designed to take the same concept and apply it to much higher frequencies. So instead of 1 millimeter wavelengths, we're looking at multi-terahertz wavelengths, so 0.1 millimeter wavelengths. And one of the first goals we've come up with is to try to use this to look for the decay of axion-like particles in dwarf galaxies. So it turns out in about 7 minutes with a rocket flight with 20 to 50 spectrometers, you can actually measure the spectrum of the 1 to 3 terahertz range carefully enough, with enough precision to determine whether or not there are lines you didn't expect. And if there are, then it's possible those could be associated with a decay of either dark photons or some other kind of axion-like particle. So the goal here is to replace the microstrip with physical cavities that are plated in superconductor, with the goal of making the loss associated very small. All right, I will skip a bunch of this. And I'll just mention there's a newly funded project called SPT-SLIM, Summer Line Intensity Mapper. And the goal here is to actually do some spectral line intensity mapping from a real telescope at the South Pole. So we're planning on something like 20 detectors, similar design to what I talked about, slightly modified to involve aluminum and local fabrication. And the goal there is basically just to measure CO lines, carbon monoxide lines, in redshift 1 to 3, which will be an important demonstration of galaxy details. Probably won't give us a whole lot of cosmology, but it's a good first step towards a larger instrument in the future. All right, sorry, I'm gone way over, but that's all I have.
Great, very, very cool stuff. So I think we virtually clap and open the floor for questions for Erik on any of the myriad topics that he's spoken about. I have one. So you know, I hadn't quite realized how broad the potential applications that you're looking at here are going, you know, ranging from millimeter wave spectrometers that are relatively, you know, and sub-millimeter, you know, things looking at that are relatively high resolution to, you know, to really not really spectrometers, just using kids as detectors, to you know, to all things in between. So how with a spectrometer, how do you observe the sky? Is it you know, I think a lot of people are used to just sitting and pointing, you know, at the sky. With CMB instruments, we always scan, raster scan, you know, because we're looking at we need a time variation, we need a modulation of the time stream. With these spectrometers, you need to scan. Is that right?
So there are two strategies we've talked about. So the Superspec instrument is actually going to have a chopper. And so the goal is to have three pixels and 2 polarizations, and you chop back and forth at 1 hertz.
But it'll be a mirror, a mechanical mirror.
Yeah, indeed.
So you are rapidly modulating between 2 parts of the sky. Okay, this is like 1980s old school CMB.
Yep. Yeah, exactly. Yeah. It's going to hum when you stand in the cabin.
Yeah.
And the goal there is basically 1 pixel on source at all times, and then you just take a spectrum.
Okay, so that's looking at sources, known sources. Okay.
Yeah.
Okay.
That's objects that have been identified in wideband cameras. The intensity mapping version. So we're actually kind of arguing about this at the moment. The version that the Time Project and some of our collaborators are excited about is basically taking a very narrow strip. So you go back and forth in by a couple of degrees, and you have an array that's aligned in elevation. So you're making a map of a very narrow rectangle,
like a scanner.
Sorry?
It's like a scanner.
Yeah, indeed.
Yeah.
And that in principle has high sensitivity, but the data analysis is a little complicated. I think the version we proposed for SPT-SLIM is actually a very small square patch. Just because then the modes in one dimension and the other are the same.
Okay, but again, you're scanning it across the sky.
Yeah, it's exactly like a.
Okay. I think Corbin is raising his hand. Am I supposed to call on people?
I don't know.
Yeah, I was going to say, it's so hard because I can't even see everybody. You know,
yeah,
right
I know
now.
that's the problem. I can't see everybody either. But I just have a really quick question. Could you reflect on the kind of what I would call the stability of these detectors? I mean, you showed this response map that's with the really pretty colored peaks all lined up and together. But of course, to get the spectrometry, but if you're really interested in the intensity, the question is how stable are those curves as a function of, say, well, anything, but basically the next time you come back, is it the same curve? I was just kind of curious.
Yeah, that's a really good question. I think the answer is that as long as the temperature at which you're operating is way below TC, everything is governed by the physical dimensions of the thing. To be honest, we've not tested that, but I'd be very surprised if it changes by more than we can measure, just based on if you're at 1/10 of the superconductor temperature, the kinetic inductance is not going to change, and the dimensions aren't going to change. So it should be within the the bandwidth that we measure.
And everything's fixed on the chip, so you don't have instability due to, I don't know, coupling between your reactive devices or anything like that.
I mean, the total amplitude certainly depends on the optics and so on. But I think the position is pretty well fixed by the chip itself. And if you decide not to read out some of them, that doesn't change where the other channels are. They just don't get read out.
Okay. Looks like we're about 5 minutes over. I don't know if we should close off questions or let people go. Actually, Eric, do you have a couple more minutes? I'd actually like to ask you a couple more questions, but I don't know if,
yeah, sure.
Yeah.
I'm totally free, but I don't hold everyone else here.
Okay, yeah. So at this point, yeah, I think what we'll do is we'll let everybody go unless they want to hear me quiz Eric.
Sounds good.
Does it get a passing grade at the end? And then
all listen to astronomy.
No. This is because I have him as a captive audience, and that doesn't happen very often.
Thanks, Eric.
Thanks for the nice talk. It was quite a this is quite a clever.
Thank you.
Clever.
Alexis, just make sure you make John the host.
Oh yeah. So if somebody could make me the host, that